So we're going to be able to write and graph basic inequalities. And we're going to start by thinking about what inequalities means. So the word inequalities is essentially the opposite of equalities, since we use that prefix in, means not equal. So we're looking at things today that are not equal. And the way that we've typically compare things in math that are not equal is by using greater than signs or less than signs. So we're going to be talking about things that are not equal today. So the first basic inequality here is the greater than sign. We see beneath it the less than sign. So in this first little piece that we're going to be doing, we're going to be talking about how the greater than sign and the less than sign can both be used to represent the exact same thing. So since it is football season, I am going to give you my example. I don't want you to copy down my example because you're going to write your own example that's going to help you visualize this and be a visual that you can take with you as you move forward. So, me being an East Bay person, I have a particular affinity for the Raiders. So I'm going to draw my little Raiders thing here. The little guy in the middle is... Alright, so the Raiders are greater than their West Bay friends, the 49ers. So I don't want you to copy this down because... And so the important thing to really take away from this is that we could also write this in a different way, and it would still have the same meaning if I turn everything around. So if I turn everything around, it still means the same thing. Right now this means the Raiders that are greater than the 49ers, but I also could say it as, well, the 49ers are less than the Raiders. And I'm not going to finish this drawing this out immediately because you're going to take a minute to write your own visualization. Now, this visualization is important for two reasons. Number one, it helps you remember. This is something that you should be able to draw and remember and visualize in your own head from here on out, something that makes sense to you. Which is why you should not have my example drawn on your paper. Because this probably doesn't make sense to you, considering your actions. Most of you don't think that the Raiders are greater than the 49ers. So you want to draw something that makes more sense to you. I've seen people talk about various different sports, use their own examples for sports teams, talk about other things that they want to do. So you're going to use your own visualization to show that you can write the same expression two different ways with inequality symbols. This will also help you visualize in the future greater than or less than symbol so you can remember which one is which. So right now you should be drawing your own examples. The next thing that we need to talk about is we need to talk about what a solution is. So at this point, most of you have a very basic understanding about what the solution to a math problem is. You understand that when you have an equation, the solution is one number. And at this point, when most of you think about solution, you think about the solution is exactly one number. Well, that's not always true. Okay? We're going to see plenty of examples today where the solution is way more than one number. So when we talk about the word solution from here on out, we need to make sure that we're thinking about the solution as being the set of all numbers that makes the statement true. And so for the equations we've been working with, there has been exactly one number that makes the solution, okay? But today we're going to look at some of these examples where that's not necessarily the case. It says Ricardo has completed more than 9 problems. Ricardo has completed more than 9 problems. So first of all, we're going to use that lesson that we've already picked out today, which is that there are two different ways to write every inequality. I have this written as x is greater than 9 for me. What's the other way that I can write this inequality and have it still have the same meaning? Isaiah? Yep, 9 is less than x. Now we're going to get to that second piece. And that second piece is thinking about, well, what is the solution to this inequality? Somebody give me one number that is part of this solution, because there isn't just one number that makes this number statement true. Give me one number that is part of this solution. Crystal?
10.
Crystal says 10. Somebody give me another number that is part of this solution. Jorge? 20. Somebody give me another number that is part of this solution. Jalen?
30.
Somebody give me another number that's part of this solution. Bradley? 15. Axel? What?
40. Oh, 50. 60.
Okay. Then let's get a little bit more creative. What about 9.5?
Yeah.
I heard somebody behind me say 9.2. 9.01. Okay, all of these numbers are part of the solution. And what we could do is we could sit here and we could talk until we died, and name numbers that are part of this solution. So what we can see here is that for this solution, there are an infinite number of numbers that are part of this solution. There's not just one number that is part of the solution. So the way that we represent this is we either represent it using the inequality that we wrote at the beginning, or we can represent it on a graph. So on a graph, I'm going to create the number line. And I'm just going to start the number line at 9 because that seems to be the central point of our solution here. And I'm just going to number a few numbers on there. Make sure I have some numbers on either side. Now, we've already said that 10 is part of the solution. We said that these numbers like, actually I'll do this in blue, 10 is part of the solution, 9.1, 9.2, like a whole bunch of those numbers in between here. We said like 20, that's way out here, 9.5, 10. Okay, so we've got a handful of these already plotted, but what we know is that everything over here, 11, 12, 13, 14 is part of the solution. And so the way that we show that all of these numbers are part of the solution is that we show a shade right over top of it. When we get over to 9, that's where we have to ask ourselves a question. I get directly to 9, and I've been shading all the way back, and I get directly to 9. Is 9 part of the solution? Keep yes or keep no. Is 9 part of the solution? Samantha, you're telling me no. Why not? Yeah, so 9 would be equal, not greater than. So the way that we represent that everything right up until we get to this 9 is part of the solution and that 9 is not, is we put this open circle. And because we put this open circle, that's why we actually call this type of inequality an open inequality. Because 9 is not part of the solution. 9 is not greater than 9. The absolute last thing that we have to make sure that we pay attention to is what happens when we get out here. Does the solution just stop when we get to the end of our number line? No. Our number line keeps going, and therefore our solution keeps going out until infinity. So this is a correct graph of our solution. It represents all numbers that are part of this solution. The last thing that we want to do is we want to be able to know how to check this. What we're checking is to make sure that we shaded the correct direction. So the way I'm going to do that is I'm going to pick a number that we shaded over the top. Remember, if we shaded over that number, we said it was part of the solution. So I'm going to take this number, like 12. I shaded over the top of 12. I'm going to plug it back into my original inequality. 12 is greater than 9. Is that statement true? Is 12 greater than 9?
Yes.
Absolutely. And that means we've shaded the correct direction. All right? Let's look at the next one. It says Ashley's net gain loss was less than 3. So what's the other way I could write this inequality? Jalen.
X is lesser
Yep.
than yes, yeah, X is greater than 3. Negative 3.
All right, so we have negative 3 is greater than x. That's the original way it was written. And Jalen tells us that x is less than negative 3 is also the other way we could write this inequality and still have the same true statement. So what numbers could it be? What numbers are part of the solution? Jefferson, give me one number that's part of the solution.
Negative 5.
Negative 5 is less than negative 3. Okay, good. Jorge. Negative 10. Isaiah, give me another. We're doing this again, aren't we? Jefferson, give me another.
Negative 4.2.
Negative 4.2. Jalen.
Negative 6.
Negative 6. Negative 12. Okay. What about negative 3.1? All right. So again, we see that same idea here. We have a whole bunch of infinite number of numbers that can be part of the solution. So what I'm going to do is I'm going to graph it. And I'm going to start with my central point is negative 3. Just going to put a few other points on this number line. And now I'm going to start to graph it. So you've already told me this negative 3.1 is part of the solution. Negative 6, negative 5, negative 10, which is way out here. So it looks like we've decided all the numbers on this side going out until infinity. So that's why I'm going to put this extra shaded arrow over here. And then I'm going to get up to 3, and then I'm going to ask myself that really important question, is negative 3 part of the solution? Keep yes or keep no, is negative 3 part of the solution? No, and so to represent that it's not part of the solution, I'm going to put an open dot. And that reminds me that this is also known as an open inequality. All right, now I want to check this. I want to make sure that I shaded the correct direction. What number can I plug in to check that I shaded the correct direction? There are lots of numbers we can plug in. So we can pick an infinite number of numbers, but what's one that you would like to use? Crystal?
Negative 7.
Negative 7. So she's come all the way out here. She's saying, hey, we shaded over negative 7. Let's plug it in. So I'm coming back to my original. Negative 3 is greater than x. So I'm going to say negative 3 is greater than negative 7. Keep yes or keep no. Is negative 3 greater than negative 7? Is negative 3 greater than negative 7? Yes, absolutely. I'd much rather owe somebody $3 than owe them 7. All right? And the last one says Ashley has at least $2. See here?
On the one on top, I went, the other one. I didn't go, like, up to negative 1 and negative 5. I went to...
Is your number line correctly numbered? Do you have the positive numbers going to the right and the negative numbers going to the left?
Yes.
okay, then yours would be shaded incorrectly, because if you shaded over something like -1, so let's see what would happen if we plug that in. This is kind of an important part. If I plug in like -1, I would get -3 is greater than -1. Is that true? No. So what that tells us is that this is not part of our solution, so we should not have shaded that over. Crystal.
Why do you shade it?
Why do we shade it? Somebody explain to Crystal why we're shading. What does that represent? Jefferson?
That all of those numbers that are shaded and below the shaded part, that means they're all equal.
Yeah, so Jefferson very quickly explains that we're representing them because we're trying to represent all of this solution without having to list every number that's part of this solution. So everything that we've shaded over, we're saying, hey, that's part of this solution. All right? X is greater than or equal to 2. What's the other way I can write it? X is greater than or equal to 2. What's the other way I can write it? Jorge. 2 is less than or equal to X. All right, so we recognize that we have that line underneath it. That means or equal to. So this symbol is a little bit different, and we're going to see how that changes our solution just ever so slightly. All right? X is greater than or equal to 2. Somebody give me one value that would make this solution true. Jefferson. He says 2.1. Oops, not 2 comma 1. 2.1. Jorge? 4.2. Crystal? Crystal says 2. 2 is greater than or equal to 2. Okay, yeah, that works. Danilo? 2.4. Really? We're not going to go 10, 20, 30, 40? We're not going to do that again? All right, that's fine. Jalen?
2.30.
2.30. Jorge? 4.60. That's actually 2 times 2.30. All right, so we've got this list going here, but instead of really wanting to list it, what we're going to be doing is we're going to go ahead and graph it. So the center point of this is 2. I'll put a few other numbers on there. And we want to go ahead and graph this. Now, we've already said things like 2.1, 2.3, 2.4, all these 4 point something. So clearly it looks like our solution is going to be everything on this right side of the equation. All the way out until infinity. So I'm going to put that extra shaded arrow over the top that says, hey, we are going out that direction until we hit infinity. Now, as we get ready to shade, we get closer and closer to closer, and then we get to 2. We have to make a decision about 2. Is 2 part of the solution?
No.
Yes, 2 is part of the solution. 2 is greater than or equal to 2. So because we had that or equal to portion, that changes our solution just a little bit. Now, if we used an open dot when it wasn't part of the solution, what do you think we should use when it is part of the solution? A closed dot. And if it was called an open inequality, when we used a open dot, because it wasn't part of the solution, what do you think we call this one? A closed inequality. Right? Because we had that or equal to portion, 2 was indeed part of the solution here. How do I check it? Is it here?
4 is less, no.
Yeah. So I'm going to come over here. I'm going to come back to my original inequality, which was x is greater than or equal to 2. I'm going to pick one of those numbers I shaded over. Zahir has suggested 4. I'm going to plug that in for x. So I get 4 is greater than or equal to 2. And I know that's true. So that proves that my answer is correct. So there are lots of small details when it comes to graphing this. Open or closed inequality. Which way am I shading? Okay? Lots of different small details to be paying attention to. On your together time. Oops.